Hello, everybody. Welcome to my presentation number 5. My name is Lauren, and today we will be talking about cellular respiration. All right, so with cellular respiration, the main pathways that we're going to kind of talk about today is glycolysis, the pyruvate dehydrogenase complex, the citric acid cycle, and the electron transport and chemiosmosis. So kind of going into glycolysis, this is the first step, first stage. What we need to talk about is the absorption of ATP to ADP. So in order for glucose to turn into glucose 6-phosphate, the enzyme hexokinase is used and a molecule ATP is used. And so that'll generate the glucose 6-phosphate and an ADP molecule. Same as fructose 6-phosphate to fructose 1,6-bisphosphate. That uses the enzyme phosphofructokinase, uses the ATP, and it'll generate ADP. In glycolysis stage 2, NADH is going to be generated, and ATP is also going to be generated. So going from the glyceraldehyde 3-phosphate to the 1,3,5-phosphoglycerate using the enzyme glyceraldehyde 3-phosphate dehydrogenase, it'll take a molecule of NAD plus and PI and turn it into NADH. And then you can see in the 1,3,5-phosphoglycerate to the 3-phosphoglycerate, through the enzyme phosphoglycerate kinase, you take an ADP molecule and it'll turn into ATP. Then the last thing with the glycolysis, another ATP molecule is generated between the phosphoenol pyruvate and pyruvate using enzyme pyruvate kinase. It'll turn that ADP molecule into ATP. All right, moving on to the next kind of complex. Pyruvate dehydrogenase complex. This is where it goes from pyruvate to acetyl-CoA to be able to, feed into the citric acid cycle. Well, while that complex is super duper important, it also yields the one FADH2 and one NADH. So you can kind of see that between here. So the dihydrolithiamide that has the FAD, and then through, is it this enzyme here? Sorry for that. My neighbor was at my door. Continuing. So the enzyme used to turn it into lithiamide and FADH2 is the dihydrolipoyl dehydrogenase enzyme. And then the next step, forming the NADH, it'll feed in NAD plus, and NADH will be produced. All right. Next big step here is the citric acid cycle. So the citric acid cycle overall will yield 10 ATP molecules, but we'll get into that math in a little bit. But so looking through here, NADH is going to be produced, FADH2 is going to be produced, and ATP is also going to be produced. So we're going to kind of start on the top right with the isocitrate to the alpha ketoglutarate using the enzyme isocitrate dehydrogenase. It'll yield an NADH molecule. And then again, right below it, from alpha ketoglutarate to succinyl-CoA, it uses the alpha ketoglutarate dehydrogenase complex, and that will yield another NADH molecule. Then the step below that, from succinyl-CoA to succinate, that ATP molecule will be produced through the enzyme succinyl-CoA synthetase. And then next step is the succinate to the fumarate. With the enzyme succinate dehydrogenase, FADH2 is produced, and then kind of go all the way up to the top between malate and oxalacetate. It'll use the enzyme malate dehydrogenase, and it'll yield another NADH molecule. So yeah, a lot going on in the citric acid cycle. And then finally, the electron transport chain. This is kind of tied together with chemiosmosis and all of that good stuff. There is a proton motive force that kind of drives everything, and it can overall yield 34 ATP. So that is a lot that is able to be yielded from that. That proton motive force will feed into those ATP synthase off to the right here. And so it'll convert the ADP plus the phosphate into the ATP here. This all occurs in the mitochondrial matrix, like the inner space membrane, like the little folds of it. All right, kind of getting into the math now. I found this super cool chart in our textbook, and it kind of shows what the yield is per glucose molecule fed into. So like if the glucose molecule is gonna get phosphorylated, it's -1. So like that's talking about the glycolysis, right? And then the second one going into the fructose 6-phosphate, it'll lose that ATP, right? Remember how we just chatted about that? This kind of sums it up into a nice little chart. So it's showing where the ATP is going to be lost and where it's going to be gained, essentially. So within glycolysis itself, because of the formation of the NADH molecules, it'll yield in glycolysis 2 ATP. Continuing next to the citric acid cycle, because the pyruvate kind of just equals itself out with the FADH and the FADH2 and NADH. So going into the citric acid cycle next, 2 molecules of ATP are gained from the 2 molecules of succinyl-CoA. Everything else kind of evens out, but so yeah. Here you can read a little bit more. The 2 molecules of NADH formed in glycolysis, it'll yield 1.5 molecules of ATP. So 2.5 ATP per 1 NADH molecule, and then 1.5 ATP per 1 FADH2. Well, that's all of the math, basically. So net yield per molecule of glucose going through the cellular respiration is 30.